So I've also been teaching D3 for I guess 3 years now, and as I've gotten more into the topic, the Truss Analyzer has come to sort of symbolize for me a problem that I see in the way we approach these classes. It's without care, students see this as a design machine rather than a design tool. In other words, they just put geometry in, apply a linear equation here, so whatever, and automatically generate failing members and a truss failure load. Problem with this is that this is making a lot of assumptions. We're bringing in a Euler's equation here, assuming a material. This is based on apparently it's based on data that we got from a specific class a number of years ago, and we're applying a linear equation to that data. One thing we would know from the study we did in the semester is that that would not be a line. The relationship between the unsupported length and the critical buckling load of a material will not describe a line if our theory is to be believed. So my point is, this is a great use of this tool, because all that's going on now is that we have geometry expressed and then mathematical equations applied to that geometry and displayed graphically. So we have the Pythagorean theorem being applied to this, to generate the lengths of these members, and then the trig that we could manually do with a free body diagram applied very quickly, so that we get these relative loads between. So a load that's if we put 100 units on the top of the truss, this member will experience 106 pounds in compression. That's really meaningless until we apply a material to it, so we can do that in a more complex way than the Truss Analyzer allows us, by bringing that data in from the Truss Analyzer and then performing calculations on it. What I did this semester was focus on creating a theoretical truss and an empirical truss. Whatever, I'll talk about that, whoever wants to hear about it. My point being that the truss that I've started kind of ragging on the Truss Analyzer in class, and so last semester or in fall of 2019, I had a student, Jack Himovitz, who's I believe a computer science major, but he really got into structures, and he was very creative on all the assignments up to the final in the truss design project. He, in addition to doing a bunch of other stuff, he designed his own Truss Analyzer. But it was, well, first of all, it did what our Truss Analyzer does. So let's just create a basic Pratt truss here. Bear with me, I'm just showing you that it is pretty easy to utilize his tool. I have to apply a load, then I calculate, and he's saying that this static Pratt truss will fail at 227 pounds, has 56.63 inches of member length. If we go and look at in my analyzer, we see we have 228 pounds, also 56.63. So, and this data came from a Truss Analyzer, so it's with my own calculations. So anyway, we're at the same point that we were in the class with the class's approach to this geometrical exercise. But then what Jack did on top of it was created an algorithm. He has a randomized algorithm that's moving these joints incrementally, and then testing the outputs to see if it's improving, and moving them toward then an optimized geometry for strength and weight. So if I hit optimize, you see that that process is occurring. And so now we're at a much stronger truss, 458, that has a higher load per inch rating. Anyway, my point is, this tool was developed within the context of D3, completely outside, of course, the requirements provided. But Jack just got into it and developed a V1 of something that's first of all better than what we're providing in class, but also really interesting and something that could be developed much further for other purposes. So again, the question is, how do we encourage Jack to do this while also keeping the class going at a pace that other students can get out of it what we want them to?